Greetings everyone, we are from Group 3 and we will be presenting our mini project titled The Seebeck Effect, a solid state approach to thermodynamic heat exchange to electricity generation.
For our abstract, our experiment is to evaluate the transient performance of a commercial SP1848-27145 bismuth telluride thermoelectric generator TEG under non-steady state conditions. So this experiment built using a low-cost or household apparatus like a paper cup hot reservoir and aluminum tin can isolators. So temperature and electrical profiles were monitored over 17 minutes. At initialization, which is T equal to 0 minute, a peak thermal gradient of 71 degrees Celsius produced a maximum power of 0.46 watts, which is at 1.53 volt, 0.3 ampere. However, rapid thermal conduction and cold side ice saturation caused the temperature gradient to collapse exponentially by 87.3%, dropping power output to 0.018 watt by the 70 minutes. A linear IV curve confirms stable operation along a 5.1 ohm load line. The results prove high fidelity thermodynamic mapping is possible with everyday materials, while demonstrating that active fluid cooling is essential to sustain long-term power generation.
The growing demand for clean energy and waste heat recovery has increased interest in thermoelectric generators (TEGs). A thermoelectric generator is a device that converts heat directly into electrical energy without any moving part. It works based on the Seebeck effect, where a temperature difference across a thermoelectric material produces a voltage. Among thermoelectric materials, bismuth telluride is widely used because it has high efficiency near room temperature. Although many studies test these devices under controlled laboratory conditions, with active cooling, real-world applications often operate without active cooling, causing the temperature difference to increase over time. Therefore, in this experiment, we investigate the performance of an SP1848-27145 thermoelectric module using hot water and ice as the heat source and heat sink. Our main objective was to study how the temperature difference affects the electrical output of the module.
Let's look at the core of our experiment, the Seebeck effect. Applying heat to one side of a material while keeping the other side cold forces electric charges to migrate. This charge movement generates a measurable voltage, which is exactly how our thermoelectric generator or TEG module works. The appeal of this kind of energy conversion is that it has no moving parts, no turbines, no fluids, just temperature difference doing the work. The specific material we use is bismuth telluride. It is heavily doped, meaning it is engineered to conduct electricity efficiently. However, this material has a major limitation at high temperatures, where both positive and negative charges carriers start at moving at the same time. They partly cancel each other out, causing the material to lose efficiency as it gets hotter. Structurally, bismuth telluride consists of layered thin sheets. Scientists can tune its performance by mixing in a small amount of selenium. A slight change to this atomic structure directly impacts the power output. But lab conditions do not equal reality. In our actual setup, we lost performance to wiring resistance, heat escaping, and the cold side warming up. Even the multimeter used to take our readings adds its own small load to the circuit, meaning what we measured was never purely the material's behavior alone. Bismuth telluride conducts heat very quickly. Because our setup lacked a cooling system, the temperature gap between the hot and the cold sides collapsed rapidly. This immediate drop is exactly what you will see in the upcoming graph.
So, moving on to methodology. The experimental setup was constructed using readily available household materials to investigate the electrical performance of the TEG module thermoelectric generator, which is the SP184827145 bismuth telluride under an impulse temperature ingredient. The module serves as the thermoelectric current. First, a paper cup was used as the hot water reservoir, while we fabricated custom brackets from aluminum beverage cans to be used as thermal management and mechanical support. And a larger primary aluminum bracket was designed to suspend the TG module securely above the hot water bath, preventing direct contact with the water. A smaller secondary aluminum bracket was positioned on top of the module to hold the ice cubes, thereby establishing the cold side of the thermoelectric device. Electrical output measurements were obtained using the digital multimeter connected to the TEG module to measure the generated voltage and current. Temperature measurements were required using the digital multimeter equipped with the K-type thermocouple because direct contact between the thermocouple and the ceramic surfaces of the operating module was difficult to maintain. The thermocouple tip was successfully manually placed on the aluminum bracket surface immediately adjacent to and in thermal contact with the hot side and the cold side of the module. This approach provided a close approximation of the temperature experienced by each side of the thermoelectric module. At the beginning of the experiment, the paper cup was filled with hot water and the primary aluminum bracket was positioned such as the TEG module was suspended immediately above the water surface. Ice cubes were then placed in the upper aluminum bracket to establish a temperature difference across the module. The hot side temperature, cold side temperature, output voltage, and output current voltage were recorded manually at 1-minute intervals for a total duration of 17 minutes. Data collection continued until the measured electrical outputs exhibit only negligible changes with time, indicating that the thermoelectric system had approached a near steady state operating condition.
Moving on our results and discussion, we investigated the transient performance of SP1848 thermoelectric generator. At the start of the experiment, the module experienced its maximum temperature difference of 721 degrees Celsius, producing a peak output of 1.53 volts and 0.3 amps, corresponding to a maximum power of approximately 0.56 watts. This indicates the energy conversion on the largest thermal gradient. Over the next 17 minutes, the temperature difference gradually decreased because the heat conducted through the bismuth telluride module, while the ice cooled reservoir warm up. As a result, the thermal gradient fell from 71 degrees Celsius to 9 degrees Celsius, causing the output voltage and current decrease to 0.3 volts and 0.0 amps. This clearly demonstrates that the thermoelectric performance strongly depends on maintaining large temperature difference. This behavior follows the Seebeck effect, where the generated voltage is directly proportional to the temperature gradient across the module. As the hot side and cold side approach thermal equilibrium, the driving force for charge carriers weakened, reducing the electrical output. At the material level, bismuth telluride acts as a semiconductor, and its electrical transport properties further contribute to the observed reduction in performance. Our experiment also had several limitations. Temperature was measured on the aluminum brackets rather than directly inside the module, introducing thermal interference losses. In addition, the absence of active cooling caused the ice reservoir to warm rapidly, while the multimeter's internal resistance affected the measured electrical output. Overall, the experiment successfully demonstrated the Seebeck effect and highlighted the that efficient cooling is essential for maintaining stable and higher power generation in thermoelectric system.
For our conclusion, this study successfully demonstrates Seebeck energy conversion using a low-cost or home-built setup. At a peak thermal gradient of 71 degrees Celsius, the TEG module generated a maximum power of 0.46 watt. However, without active cooling, rapid thermal solution collapsed the temperature gradient by 87.3% over 17 minutes, continuously reducing power output. A linear IV curve confirms stable operation along the multimeter's internal 5.1 ohm load line. For future iterations, should incorporate an active fluid cooling loop to sustain the thermal gradient and a variable rheostat to map the true maximum power curve.